let's look at a quick, easy way to calculate the maximum number of electrons in a main energy level. Now, you could look at your periodic table and you could actually count this out. Like you could count in each energy level, first, second, third, all the way through seventh. And you could theoretically count out them physically on the periodic table. But this is a quick way that we can calculate the maximum number of electrons found in a main energy level or that can fit in an energy level. It's the formula that we use. And the formula is called the 2n squared rule, where n is your energy level. Now, we just learned about quantum numbers, the n, l, m, and s. In this case, n is your principal quantum number, and remember the n represents the energy level within the atom. So let's just apply this to each energy level. So if I were to say in the first energy level, n equals to 1, what's the maximum amount of electrons that can fit in that energy level? Well, of course, you can look at your periodic table and you can look in the first energy level, and there's hydrogen and helium. So there's 2 elements, theoretically 2 electrons that can fit in the first energy level. This one's pretty easy, but let's use it with the 2n squared rule. 2 times 1 squared. Now remember, order of operations, you have to square, do your powers first. So that's going to give you 2 times 1, which is 2 electrons can fit in the whole first energy level of your atom. That's why when you draw your Bohr model, the first energy level only can hold 2 electrons. Let's look at the second energy level. Plug it into the 2n squared rule, 2 times 2 squared. That's going to give you 2 times 4, which is 8 electrons. So remember when we were drawing our Bohr models, we could only put 8 electrons in the second energy level. And this is why quantum theory correlates to that. Third energy level. Now this is how we know, or one way we know, that the d orbitals, the d electrons, come in the third energy level. You put into the 2n squared rule, 2 times 3 squared. That's going to give you 2 times 9. Well, that's 18. Now remember, in the third energy level, you have the S, the P, and the D block. The D block comes in the third energy level, which are 10 of these electrons that we see here. Let's look at n equals 4. So 2 times 4 squared. That's going to give you 2 times 16, and which that gives you the 32 electrons. So if you look at the S, P, D, and F block, remember the F block comes in the fourth energy level. So that's 14 more electrons that we're talking about. The fourth energy level can hold up to 32 electrons max. Now, we don't have enough elements that actually exist to fill up the entire seventh energy level. But theoretically, if we were to look at what would be the maximum amount of electrons that could fit in the seventh energy level, you're going to plug into the 2n squared rule. And that's going to give you 2 times 7 squared, which is 2 times 49. And if you multiply 2 times 49, we get 98 electrons could fit in the seventh energy level. Now that's through quantum theory. All right, so electron configurations. Electron configurations, this is a way that we represent the location of all of the electrons in our atom. Now, when we do our quantum numbers, N, L, M, and S, this is what I call the address of our electron. It takes 4 quantum numbers to get the address of only 1 electron. N tells you the energy level, L tells you the shape of the orbital, M tells you the mailbox number, which is really the magnetic quantum number, the position in space, and S tells you the spin direction. It takes 4 quantum numbers to give you the location of 1 electron. Well, electron configurations represent where all of the electrons are in your atom. It's actually much easier, in my opinion, to come up with, to write the electron configurations, and it's really more helpful to us to understand the electron structure in your atom. Now, there are 3 rules that we have to follow when we write our electron configurations. The first rule is the Aufbau principle. And the word Aufbau is a German word, and it means to build. So if you remember that, that will help you remember the definition or the rule. This tells us an electron will fill the lower energy orbitals first. They have to fill the lower energy level orbitals first. Just like if you're building a house, you have to build the foundation. So you have to fill up the first energy level before you go to the second. And then once you fill up the second, you can go to the third. So you have to build your foundation. That's the Aufbau principle. The second rule is called Hunds Rule. And this is the rule that tells us the electrons will fill their subshells. Y'all, the subshells are when we draw we drew the boxes, the orbital notation. These are the boxes that we drew when we did quantum number M. The subshells, they fill their subshells separately before they pair up. So they're going to be single before they pair up with their Hunds Rule. I'd remember if you look at the p orbital, I said when you fill up your p orbital, if you have your 3 subshells, then I said all the wives have to come home first, up, up, up. That's spinning clockwise. They all got to fill the subshells separately before they pair up. And when they pair up, they have to pair up with opposite spin, down, down, down. So they're going to be single before their honeys come home. That's Hunds Rule. And then the last rule is called Pauli's exclusion principle. And this basically says no 2 electrons can be in the same place at the same exact time. Just like no 2 people can be in the same exact place at the same exact time. All right. So when you're writing electron configurations, we're going to represent the energy level with the N quantum number, the orbital shape, and we're going to be using like S, P, D, and F for this. And then there'll be a superscript. The superscript represents the number of electrons in the orbital. So we're going to be using the N quantum number, S, P, D, or F, depending on the shape of the orbital. And then as a superscript, we're going to put the number of electrons in each orbital. So your electron configuration will look something like this. Now this is for a very short one. Your N, your orbital shape, and an asterisk. So for example, I'll just do an easy one here. We're going to do helium's electron configuration, and we'll learn how to do this next class. You would put 1 because he's in the first energy level, S because he's in the S block, it's the S orbital, and he's the second one over, so as a superscript you put 2, 1s2 would be helium's electron configuration. If we want to do hydrogen, hydrogen is in the first energy level, S-shaped orbital, and it's the first element, so 1s1. The superscripts do tell you the number of electrons in each orbital. Next class, we're going to actually go through, write several electron configurations, longhand and shorthand.